You've likely experienced this. You spend hours, maybe days, carefully prepping documents, chunking them just right, loading them into your vector database. Then you ask your shiny new AI agent a pretty simple, direct question. And you watch, maybe with that sinking feeling, as it confidently spits back an answer that's, well, completely irrelevant. Or maybe just plain wrong. That specific moment of dismay when your R agent just completely misses the point.
Yes, that feeling. We've absolutely all been there. It's so frustrating.
Welcome to the deep dive. Today, we're really going to dig into that exact challenge. It's pretty widespread in AI development, actually. How do we turn those frustrating, sometimes scattershot information retrievers into real precision knowledge machines?
Precisely. Yeah, it's all about fixing arguably the #1 flaw in retrieval-augmented generation agents, our edge agents. We're going to unpack two really powerful techniques, reranking and metadata enrichment. Think of them like superpowers for your AI.
We'll explain why your ag agents might be failing you, and then, importantly, give you a practical blueprint to fix them. We'll show how tools like, say, n8n and Supabase make this doable. We'll even walk through a specific example using, of all things, golf rules.
So what does this all really mean for building AI you can genuinely rely on?
Okay, let's get into it. Let's start maybe with the basic flow, the fundamental steps in most standard RG setups. You have your source document, right? A PDF, maybe something else. It gets broken down into smaller bits, chunks, as they're called.
Right. And each of those little chunks gets turned into a numerical vector by an AI model. It's kind of like a mathematical fingerprint of what that chunk means. These fingerprints, these vectors, they get stored in a special kind of database, a vector database.
Then, when a user asks a question, the question itself gets turned into a vector too. The system hunts through the database for the vectors that are mathematically closest. That's the nearest neighbor search part. The text chunks linked to those closest vectors get pulled out and fed to a large language model, an LLM, which then writes the final answer. It sounds pretty logical, doesn't it?
It does sound logical on paper, but here's the real kicker, the critical point where it often breaks down. It's the assumption that mathematically similar always means contextually relevant. That's the flaw. It's like, imagine asking about payment terms for a service, and the system brings back stuff about terminating a contract. The words might overlap a bit, terms, terminating, but the actual meaning, the context, completely off. And that's why a lot of promising AI projects just kind of fizzle out. They don't deliver reliable answers.
Okay, so what's that core assumption basic RG systems make that often leads straight to irrelevant answers?
Basically, it assumes mathematical similarity equals true relevance. And that's just not always true.
Right. And this is precisely where re-ranking comes into play. It feels like a game changer. How exactly does it tackle that core problem you just laid out?
Okay, think of re-ranking like adding a super smart quality control manager to your information assembly line. Instead of just grabbing the first few things off the belt that look roughly right, it takes a much bigger batch, like a whole pile of potential candidates, and then it carefully inspects each one for how well it actually fits the original request.
Okay, so you cast a wider net initially, but then you apply a much more discerning filter. Can you maybe contrast the old way versus this new re-ranked flow?
Absolutely. So the traditional RU flow, user asks a question. The system grabs maybe the top 3 or 4 nearest vectors based purely on math, sends those straight to the AI. It's often a bit of a hope and pray method, honestly. You just hope those top few are good enough. But with the re-ranked flow, the vector search still happens first, but you tell it, hey, bring me back more options, maybe 10, 20, even more candidate vectors, a wider net. Then this bigger pool of candidate chunks gets passed to a specialized re-ranker model.
And what's really interesting here is that the re-ranker's only job is to look at that bigger set of chunks and compare each one directly against the original user query. It's not just doing math similarity again, it's looking for genuine contextual relevance. It assigns a score, like 0.0 to 1.0, saying how relevant is this really? And then, crucially, it throws away everything except the very top scores, maybe the best 3 or 4. Those are what finally go to the LLM. It massively boosts the quality of the input for the AI.
Yeah, it ensures the AI gets only the most relevant stuff, makes the final answer way, way more accurate. And, this isn't just theory. It's actually surprisingly straightforward to put into practice, especially using tools like n8n that handle a lot of the complexity.
Right. The main thing you need first is just a basic ARG workflow already set up. Maybe you're already using something like Supabase as your vector database. So let's walk through the actual steps to add Cohere re-ranking. First up, you need an API key from Cohere. You'd go to cohere.com, sign up. They have a pretty generous free tier, which is great for getting started. Grab an API key, Maybe name it something clear like n8 ranker key.
Okay, step one, get the key. Then what?
Then you need your vector database set up. Let's stick with Supabase. You'll create a table, let's call it documents, to hold your chunks. It needs a few columns, like an id, maybe an integer, the actual content as text, a metadata column, probably JSON-B format for flexibility, and of course the embedding column itself, which holds the vector data type.
Got it, table structure. Then connect it in n8n.
Exactly. You go to your Supabase Vector Store node in your n8n workflow. Now, this bit's important. You need to find the limit setting. By default, it might be set low, like 4 or 5. You have to crank that up, set it to maybe 20. That's casting the wider net we talked about.
Ah, okay. Increase the limit first.
Yes. And then you just flick the switch. There's usually a toggle labeled Rerank Results. Enabling that makes new fields appear for the reranker setup.
Makes sense. And the final step?
Just configure those new fields. You'd select Cohere as the provider, paste in that API key you got earlier, and pick a reranker model. Rerank v3.5 is a good one. Save it, and you've basically integrated reranking.
Okay, that does sound pretty doable. But it brings up an important question. Why is it so critical to increase that initial limit in the vector store node before the re-ranking happens? Why not just re-rank the default 4 or 5?
Because the reranker needs a decent pool of candidates to show its value. If you only give it 4 options, maybe none of them are actually that relevant. By giving it 20, you significantly increase the odds that some truly relevant chunks are in that initial pool for it to find and promote. It needs options to work its magic. Okay, so before our RAG agent can even start answering questions with re-ranking, we need to actually feed it knowledge, build its brain, so to speak. That happens through a data preparation workflow.
Right. This is the back-end pipeline. It's what takes your source document, like that PDF of golf rules, processes it smartly, and loads it into Supabase, ready for the agent to use. This is how you build the actual knowledge base.
So the process might look something like this. First, you get your source PDF, maybe download it. Then you extract the raw text out of it. And here's a crucial part, structuring that raw text. You could use, for instance, a JavaScript code node in n8n. You might write a little script or even get AI to help write it.
Oh, interesting.
Yeah, a script that looks for patterns, like rule number X in the text, and uses those patterns to split the document into meaningful JSON objects. Each object might have, say, a rule number, a rule title, and the full text for that specific rule.
Ah, so you're breaking it down logically, not just by random character counts, and adding structure right away. Then presumably you load that structured data.
Exactly. You load that structured data, and importantly, you add metadata during this step, like that rule number you just extracted, maybe a document type like official rules, maybe a date created.
Then you generate the vector embeddings for these nice structured metadata tagged chunks. You could use an OpenAI model like text embedding 3 small with your OpenAI key. And finally, you upload the whole package, the structured text, the metadata, the embeddings into your Supabase table. This careful prep work is really foundational.
Absolutely. If you think about the big picture, the quality and thoughtfulness you put into this data preparation stage, that directly dictates how reliable and accurate your entire RAG system will be later on. It's the bedrock.
Okay, so why is strategic data preparation considered the foundational step for a good RAG agent?
Because good data prep ensures you have a structured, accurate knowledge base. That's absolutely critical for the AI's performance down the line. Let's make this concrete. Let's talk about that golf rules agent again. It was built from a 22-page PDF covering 28 distinct golf rules.
Right. So the test query we used was, how is the order of play determined in golf? Simple enough question. Now, without re-ranking, a basic argue system, just looking at word similarity, it might easily grab chunks talking about penalties or maybe equipment rules. Why? Because the word play shows up in those contexts too. That leads to irrelevant bits getting mixed in, and you end up with a confusing, maybe incomplete answer.
Okay, but then we switched on re-ranking. The Supabase node first did its job, fetching 20 chunks that were mathematically similar to the query casting that wide net. Then the Cohere reranker stepped in and evaluated each of those 20 chunks for true relevance to the question about order of play.
And the results were really clear. Chunk 1, which talked about match play order, got a high score, 0.877, super relevant. Chunk 2, explaining stroke play order, also scored well, 0.642, still very relevant. Chunk 3 was about provisional balls, less directly relevant but somewhat related, scored 0.57. But crucially, the other 17 chunks, they had much lower relevant scores. The re-ranker basically said, nope, these aren't really about the order of play, and discarded them. Only the top ones went forward.
And the AI's final answer, built only from those top-scoring, truly relevant chunks.
Yeah.
It was perfect, it was comprehensive, accurate, detailing both match play and stroke play order. It even offered more details if needed. The re-ranker acted like this incredibly precise filter, cutting out all the noise.
Yeah, and what's really cool, especially in a tool like n8n, is the transparency. You can actually look at the logs and see it happen. You see the query, you see the initial 20 results pulled, you see the re-ranker scores for each one, and you see exactly which top chunks got selected to build the answer. Makes troubleshooting and optimizing so much clearer.
It's really powerful to see. Makes you think. Whoa, imagine applying that same level of precision, that same transparent filtering, to something massive like a billion complex scientific papers. The potential is just huge.
So what was the key difference the re-ranker made in the golf agent's answer?
It precisely filtered for true relevance, which directly resulted in a comprehensive and accurate answer.
Okay, so re-ranking boosts relevance significantly. But you mentioned metadata earlier, saying it brings surgical precision. What exactly does that mean in this context? Right, surgical precision. It tackles a different but related problem, what we call the chunk-based retrieval problem. Think about it. A single logical piece of information, like golf rule 3 on stroke play, might actually get split across several different text chunks when you do the initial document processing. It just happens sometimes based on length or structure. Now, without metadata, if you ask the agent, tell me everything about rule 3, the system just does its usual vector search based on the words in your question. It might find some chunks related to Rule 3, but it could easily miss other crucial parts of that same rule if they happen to land in chunks that don't seem mathematically similar enough to your question. You get fragmented information.
I see. The information is in the database, just scattered across chunks that the basic similarity search might miss. So how does tagging every chunk with structured info, like a simple rule number, 3 tag, fix that fragmentation?
It's simple but powerful. By adding that rule number, 3, tag to every chunk that contains any part of Rule 3, you give the system another way to find information. Now, instead of just relying on semantic similarity to the question, the system can be told, hey, retrieve all chunks that have the metadata tag rule number 3. Boom! It instantly pulls together the complete context for Rule 3, no matter how the text was chunked or how similar the individual chunk content is to the query itself. It ensures you get the whole picture. It's like giving every piece of info a precise address.
Okay, that makes a lot of sense. So how do we actually add and then use this metadata effectively, say, within n8n? You said sort of a two-step thing.
Yeah, 2 main parts. Step 1 is adding the metadata during that data preparation phase we talked about earlier. When you're processing your documents and getting them ready for the vector database in your data loader node, you explicitly add these key value pairs. So along with the text content, you'd add fields like rule number, 1, document type, official rules, date created, 2024-01-15, whatever makes sense for your data. That metadata gets stored right alongside the text chunk and its embedding.
Got it. Added during prep. And step 2, you mentioned a smart way to extract it.
Right. The smart way avoids manual labor. Instead of manually figuring out which rule is which, you can leverage AI itself. Take the raw text from your golf PDF, for example. You could go to an AI chat tool like ChatGPT or Claude and give it a prompt like, hey, help me write some JavaScript code for an n8n code node. This code needs to take this big block of text as input and split it into separate items every time it finds the pattern rule followed by a number and a colon, like rule X. For each item, extract the rule number and the rule title. The AI can often generate perfectly usable code for you. You paste that code into an n8n code node, and boom, it automatically parses your document into structured items, each already tagged with its rule number and title. Super efficient.
Wow, using AI to help structure the data for the AI. Clever.
Exactly. And then you can get even more advanced with dynamic metadata filtering. Imagine this. A user asks, tell me about Rule 8. You could have a first AI agent whose only job is to analyze that query. It recognizes the user wants a specific rule and outputs just the metadata filter needed, rule number 8A. Then, your main OG agent uses that specific filter in its Supabase query, maybe alongside the vector search, or maybe even instead of it for such a direct query. That's surgical precision, targeting exactly the data you need based on the query's intent.
Okay, so the smart way to add metadata involves using AI to generate code that automatically extracts and tags that structured data from your documents.
And the potential uses for this kind of metadata filtering, they go way, way beyond just golf rules. Honestly, it's like a superpower for almost any business data you can think of.
Yeah, I could see that. Give us some examples. How would this apply in, say, a business context?
Okay, imagine you record and transcribe all your team meetings. You could add metadata like .date, 2024 Z620, participants, John, Sarah, project.website or design. Then you can ask your AI agent, what did we decide about the homepage navigation during the website redesign meeting Sarah attended in June? The metadata makes that possible.
Or for legal documents?
Yep. Client contracts could have metadata like client name, Acme Corp, document type, MSA, status, active, renewal date, 2025-0301. Imagine querying, show me all active master service agreements for Acme Corp that are up for renewal in the next 6 months. Super targeted.
And maybe one more, like for technical docs.
Sure, a technical knowledge base could use tags like topic, API authentication, language, Python, library version 2.1, difficulty advanced. Then a developer could ask, find advanced Python examples for API authentication using library version 2.1 or later.
Wow. Okay. When you step back and look at it like that, metadata really does fundamentally change how you interact with huge piles of unstructured text. It lets you query it almost like a structured database.
It's a total game changer. It unlocks that database-like precision for messy, unstructured data.
So what kind of really new search capabilities does metadata filtering unlock for businesses?
It enables these highly specific, almost multi-dimensional queries across large, diverse data sets that were previously just impossible.
Okay, so if we think about building one of these really robust RAG systems, not just a basic one, but one with re-ranking and metadata, thinking about it as a whole project, we can probably break it down into maybe 3 distinct phases.
Yeah, I think that makes sense. Phase 1 has got to be data preparation. And we can't emphasize this enough. This phase is critical. It covers everything from getting the documents in, ingestion, to chunking them strategically, ideally along logical breaks in the content, not just random character limits. Then the AI-assisted metadata extraction we talked about, storing it all neatly structured in your Vector DB. And, vitally, quality validation. You have to check that the chunks and metadata are accurate before you build on top of them. Garbage in, garbage out, right?
Garbage in, garbage out. Okay, phase 1, solid data prep. What's phase 2?
Phase 2 is what I'd call intelligent retrieval. This is the main workflow the user actually interacts with. It starts with analyzing the user's query, then potentially applying those dynamic metadata filters if the query calls for it. Next, doing the vector search, but retrieving that larger pool of candidates, remember, like 20, followed immediately by re-ranking to score those candidates for true relevance. And finally, feeding only the best, highest-scoring chunks to the LLM to generate the actual response.
Okay, prep, then intelligent retrieval. What's the third phase? Is it ever really done?
Good question. No, it's never truly done. So phase 3 is continuous improvement. A good RG system needs ongoing care and feeding. This means monitoring things like the relevance scores the re-ranker is producing. Are they consistently high, or are there queries where it struggles? Analyzing the kinds of questions users are asking, maybe that gives you ideas for new, useful metadata tags to add. And definitely integrating user feedback. Even a simple thumbs up, thumbs down, was this answer helpful? On the responses can help you pinpoint areas that need refinement. You know, I still wrestle with prompt drift myself sometimes, getting the LLM prompts just right. So this continuous improvement loop, it really is vital for making sure the system stays effective long term.
That makes perfect sense. So thinking back to phase 1, data preparation, what would you say is the single most critical aspect there for the whole system's success?
Quality validation, hands down. Ensuring the accuracy of both the text chunks and the metadata you extract is absolutely paramount. Everything else relies on that foundation being solid.
As people start building these more advanced RAG systems using re-ranking and metadata, are there common mistakes or pitfalls they should watch out for?
Oh, definitely. There are a few classic traps people fall into. Knowing them up front can save a lot of pain later.
Okay, let's hear them.
First big one, over-engineering metadata. You get excited about tags and create like 50 different metadata fields right at the start, but most of them never actually get used in queries. The fix. Start simple. Identify maybe just 2 or 3 really key fields based on how you think people will query. Add more only when you see a clear need based on actual usage patterns. Don't boil the ocean initially.
Okay, start minimal with metadata. What else?
Insufficient re-ranking candidates. This is running the reranker but only giving it the default 4 or 5 results from the initial vector search. Remember, the reranker needs options. You've got to increase that initial retrieval limit in your vector store node, get it up to at least 15 or 20. Give it a good pool to choose from.
Right, feed the reranker properly.
Any others? Yeah, related to that. Ignoring relevant scores. Just because the reranker puts something at the top doesn't mean it's actually good enough if its score is really low. Don't just blindly pass the top 3 results to the LLM. Implement a score threshold. Say, only use chunks with a reranker score of 0.5 or higher. Filter out the low-confidence results even if they're ranked highest.
That's a smart refinement, setting a quality bar. And the last one.
Static metadata schemas. This is defining your metadata structure once at the beginning and then never revisiting it. Your data sources might change, the kinds of questions users ask will definitely evolve. Your metadata schema needs to be treated like a living document. Review it periodically, adapt it, add new fields, maybe retire old ones. Keep it relevant to how the system is actually being used.
Okay, those are great points. Why is it so crucial, do you think, to actively avoid these specific pitfalls when you're trying to build a RAG system that people can actually trust?
It really comes down to engineering user trust. Every time the AI gives an irrelevant or nonsensical answer because of one of these issues, that trust erodes. Avoiding these pitfalls is about building a system that is consistently reliable and useful, which is the only way users will keep coming back to it.
Makes sense. So looking at those pitfalls, which one do you think is maybe the most damaging to a RAG system's ability to adapt and stay useful over the long term?
Ooh, good question. I'd probably say static metadata schemas, because your data and user needs will change. If your metadata structure can adapt, the system's ability to precisely retrieve relevant information will degrade over time, no matter how good the other components are. Adaptability is key.
So let's bring it all together. What does this really mean for you, the learner, trying to build better AI? We know basic RAG agents, while exciting, can often feel, well, a bit clumsy, a bit hit or miss. But what we've seen today is that with intelligent design choices, they can transform into something much more powerful.
Exactly. It's that combination, casting a wider net initially, retrieving maybe 10 or 20 candidates, then applying that smart, intelligent re-ranking to score them for true contextual relevance, and then layering on strategic metadata, filtering for that surgical precision when needed, that synergy. That's what creates a RAG system users can actually trust, rely on, and get consistently accurate answers from.
It feels like a shift from just sort of hoping the AI gets it right to actively engineering this system so that it's much more likely to get it right. These techniques, re-ranking, smart metadata, they offer immediate, tangible ways to improve your AI agent's accuracy and overall usefulness.
Yeah. Your RG agents basically just got superpowers. Seriously. It's time to move past the frustration phase and start empowering your AI to really perform at its best.
And for you, the listener, this provides a clearer path forward, a path towards AI interactions that are deeply informed, highly accurate, and capable of cutting through the sheer volume of information we all face.
So, here's a thought to leave you with. Think about the data you interact with every single day. Your emails, your documents, transcripts, articles. What structured insights are currently just hidden inside all that unstructured text? Waiting for intelligent metadata to unlock their real power, their true utility for you.
We really hope this deep dive has given you not just a clearer understanding of these concepts, but also a practical blueprint you can use to start building more intelligent, more reliable AI systems yourself. Until next time, Otiro Music.